So next one, we talk about a sorting algorithm. So in fact, for this chapter, we will not cover all the sorting algorithms. We'll only cover heap sort and also introduction to sorting. So for these slides will be the introduction for sorting. So why we want to cover this one, the general introduction about sorting. The main reason is that you may hear before many sorting algorithms. For example, like insertion sort, merge sort, we have learned in the previous module, and the quick sort, bubble sort, you may hear before, and the heap sort, shell sort, which will be covered in this module, and also radius, RADIX, radius sort based on the probability. So chapter 5 will provide the basic knowledge for this sorting algorithm, but since we haven't have time to cover this chapter, maybe we will not learn this one as well. And also some new sorting algorithms you may hear before. So the question is that since we have so many sorting algorithms, then you may have a question. If you have problem, which sorting algorithm will be the best? How to choose? How to choose? How to compare? Okay? If you develop a new, how to compare with the existing one? If you don't want to develop new, you want to choose from existing sorting algorithms. There are so many choices. You don't want to implement each of them and then compare, correct? You need to do theoretical analysis first. What's the complexity it will be for this problem? So you need to have some information about each sorting algorithm. Means we need to do evaluation, correct? So this chapter, the introduction, this slides will give you an introduction about sorting algorithms, how to evaluate, and how to do comparison, and also how to group, like these things. Okay, so let's look at the first thing. So that means if we can build a general, or you can think about high-level mathematical model for sorting problems, seems it's better for us to generalize or to group different sorting algorithms, correct? That means all the sorting algorithms, they are doing these things, but they will do this in different ways, and then that's why these algorithms are a group, form one group, other algorithms form another group. For example, like insertion sort, shell sort is insertion based, and heap sort and selection sort, they are selection based. So that means you can group them, and then okay, you may first decide which group you want to have based on my current question. For example, my question is whether we have most of them sorted or only a few are sorted, and what's the data structure to hold the data you want to sort. So based on these things, you may choose the better group, and then within the group, you choose the best algorithms. So that's the reason we want to cover this introduction. Okay, let's look at first question. We want to build a mathematical model for sorting. So based on your understanding, what is sorting? Just consider. Mainly, you can think about, okay, unit sorting is like sort a list of numbers. They are saved in an array. But maybe sometime we want to sort not numbers, sort alphabetical letters, or strings. Sort the strings words in alphabetical order. So that means the sorting can can be applied on numbers, but it also can be applied on many other things, as long as they are sortable. Okay? So this will be the first thing. What is sorting? Okay, how to define sortable? Let's look at the definition for this sorting. Okay, the first one, you have a list of records. We didn't say it must be numbers. Okay, records. So records can be numbers, but it also can be just like a record contains numbers or contains sortable keys. So we want to sort the records based on the keys. So let's look at the second one. So each record Ri has a key Ki. So that means that you want to sort based on the keys. So that means, of course, maybe the records contains a lot of information, like a student's record, but we want to sort according to some properties. So that properties which are selected for sorting, we say they are keys. Keys means you can use this key to retrieve or to unlock something, unlock a record. You can sort a student's record based on the names, based on the number of credits, based on the enrollment date, enrollment year, and semester. So you can sort accordingly. Okay? So this is the thing we want to look at. Okay, we want to sort according to which key. And then second one, possibly other satellite information. So that means that this record may have other things which we don't care of, we don't pay attention to, but we only pay attention to the key. Right? We want to talk about this one. But once you have the key, you also know the record. So we sort the records as a whole, but we based on the keys to sort them. So let's look at how to define sortable. So the last paragraph will define the sortable. So sortable here, we define a relationship. We call it the ordering relationship. Ordering relationship, that means any two keys, they are comparable. Whether you are larger than the other one, or you are less than the other one, or you are equal to the other one, you have only one of the three choices to assign the order or the relationship between these two keys. You cannot say these two keys, we don't know their relationship is unknown. If like that, we say this is not a sorting problem, because there's some keys, means there are some records which we don't know how to sort them, how to rank them. Okay, so let's look at how to define an ordering relationship. So here you can find we are not use this like a less, okay? But this is like, in fact, is just like an order relationship. Okay. In discrete mathematics, we have a name for this one. We call I think some name. Maybe I cannot recall, but just like some, you can think about it is like a order relationship. Okay. The first one. So this one is about trichotomy. Tri means three. So for any two keys, A and B, exactly one of A less than B, A equal to B, or A larger than B is true. That means you must be one of the three relationships, cannot be any of others. We can use less, equal, or larger to represent the relationship between any two keys. So this is the first property. So that keys must meet this property, the trichotomy. The second one, why we can order, in fact, we don't need to compare one with all of the others. We may only to compare some of them, and then we can rank all of them. Why? Because we have this second property called the transitivity. So A is less than B, B is less than C, then A is less than C. So this is called transitivity. So that means as long as you know, okay, A is less than B, B is less than C, then you can rank A, B, C in the order A, B, C, right? Because we have this transitivity. We know if A less than B, B less than C, then A is also less than C, right? So this is transitivity. So we don't need to compare A and C in a explicit way, but we can use the transitivity property to deduce this relationship. A is less than C, so A must be ranked in front of C. But A is also less than B, so A is ranked in front of B. And then B is also less than C, so B must be ranked in front of C. Then we have this two in front of a relationship, but B is the bridge, so we can rank A, B, C in order. Okay, so if they meet these two relationships, we said this less or equal to is a total less is the ordering relationship, and then less or equal is a total ordering, or we call it linear ordering on the keys. Okay, so that means total ordering includes all the numbers, all the keys, and also all the relationships. So here we only use less or equal to. So that means in default total ordering we use which order? So ascending order or descending. Based on this one is default one is ascending, correct? From smaller one to big ones. Okay, this one we defined sorting as a mathematical model. Okay, it's like this one. We sort based on keys, and then the keys meet the ordering relationship, which contains trichotomy and transitivity properties. Okay, let's look at what is sorting. Right? Just now we talk about key and then their relationships. So what is sorting? So considering the keys, you just want to sort all the keys based on some order. So finally, you will rearrange the order of the keys and their also corresponding records. So in fact, you just want to do a permutation of the order, correct? The places, the positions. So we said is determine a permutation pi P1 to Pn of n records that puts the keys in non-decreasing order. This is the default order for sorting, non-decreasing. So kp1 less than kp2 less than less or equal to kp3 and so on, less than till the end, less or equal to kpn. So that means you find a position permutation and then put all the keys in the appropriate order to make the inequality relationship holds. Kp1 less or equal to Kp2 and so on. That means that based on the keys, they follow from small to biggest order. So this is sorting. So for example, initial order is 1, 2, 3, 4, 5, and then after we do the sorting, you got 5, 4, 3, 2, 1. Okay, that means you got a permutation of the order. So which one put in which location, correct? Let's look at the permutation. So permutation, we didn't add new numbers. We just only change their order. Okay? We just change their change their order, numbering. For example, a one-to-one function from 1 to n on itself. So that means you have n numbers. You permutate their relationships, their places, their ordering. You get another ordering. So for this one, because if we learned the permutation before, okay, we know in total you have n factorial of n distinct permutations for n items, because that's n by n minus 1 by n minus 2 tier 1. Because when you choose the first position, you have n choices, and then in the remaining n minus 1, you put them into second position, you have n minus 1 position, choices, possibilities. So on and so forth. You get n by n minus 1 by n minus 2 tier 1. So that's a factorial of n. So this is about a permutation, right? So that means in the beginning you have the ordering is from A1 to AN, so 1 to n. And then finally you get another permutation. You may get n minus 1, n minus 2, n minus 3, totally different, okay? So that's the permutation of the ordering. So the order is the main concern, not changing the contents, not changing the records, okay? You just rearrange the order, just like we want to rank people. We don't change the people, okay? Still the same people, but we just order them, we just rank them in different places. So this one to be here, this one to be there. So that's the idea. We only change their, you can think about n is an external property, not an internal property, okay? We don't change its content. We change the order, change the place. Okay, so let's look at another, just like a terminology rank. This terminology rank means you can think about just like assign a property to a record, and then give a property to indicate its ranking position. So for example, we define this one as giving a collection of n keys. We have n keys, we want to rank them, okay? The rank of a key is the number of keys that precede it. So how many keys are in front of the current key? Then the rank of that key is the total number of the keys that are in front. So just the rank is equal to the total number of numbers or number of keys, total number of keys that are in front of it. So for example, if we rank 1, 2, 3, 4, 5, okay, what's the rank for 1? There's no numbers in front of 1, correct? Because 1, 2, 3, 4, 5, after sorting is still 1, 2, 3, 4, 5. So there's no numbers, no keys are in front of 1. So the rank of 1 is 0. And the rank of 2 is 1, correct? Rank of 3 is 2. Rank of 4 is 3. Rank of 5 is 4. So this is the simple example. So that is rank of kj is equal to, so this is some math definition, correct? This means the number of numbers. So we use this definition. So it's we call this like just the number in a set, okay? So it's ki and then ki less than kj. So how many keys are less than kj in this set? And this is the number of elements in this set. So that's rank. So if the keys are distinct, then the rank of a key gives its position in the output file. Okay, could you just think about a ranking algorithm or sorting algorithm based on this idea? Because if the keys for each key we can find its rank, then we can directly put it in the correct position. Is it correct? So could you find a rank for each key? That means I find how many numbers are smaller than the current one. That's the rank, and then you can order accordingly. If you use an array, that's the index, correct? Index of the array is equal to the rank. For example, 1, 2, 3, 4. 1, the rank is 0, so you put this one into the A0. Okay. But how about this complexity? Is it quick enough? Depends on your design, correct? So how many loops you want to have, you will have. Okay, anyway, here we define some other important thing. The inheritance of sorting, in fact, is just a permutation of the orders. And then rank is assigned to each key to indicate its position. So this is the thing we want to learn here. Okay, in the first two slides, we defined sorting. So now we look at some other terminologies in the sorting problem. The first one is the first pair is the internal and the external. So for internal, external, this is easy to understand. Internal, cat, that means in the memory. External means not in the memory. Okay, so if you sort the problems based on all the data in the memory, that's what we call its internal sorting algorithm. So the file is stored in the main memory and can be randomly accessed. But external, you have to load into the memory and then do sorting, right? So the file is stored in secondary memory. Usually is a hard disk, right? Also can be other external devices. Okay, storage devices, for example, portable drive or even tape and so on, right? And can be accessed sequentially only. So this is the difference. So that means if you want to sort based on the external way, you have to use a physical way to access data. Just first position to that first rotate the disk, and then position to that location and then access. So that will be a bottleneck of the sorting. So when you design algorithms, you need to consider this one, especially like some embedded system, they may not have enough memory. But if you save the data in external storage, so you need to load them from the external because you cannot perform the calculation on external memory, right? External devices. You have to load them into memory first. So this one will be important consideration when you design the algorithm. Okay. So that does not mean every time we need to find the best algorithms. But for what situations we also need to consider this one. It is general or it is only applicable for random access. So if it's serial access, it may have a lot of drop in the performance. Okay, because that requires a random access like an array. We need to access each number. But if it's sequential access, for example, if the sorting algorithm is designed based on a linked list, okay, seems that will not have much impact on the performance, because when we read the data, we also do in a similar way, sequential. So linked list also can only do sequential access. You cannot jump, correct? You must go from beginning the node, the head, to the next, to next, to next. Okay. So consider all of these things together. So next one, we want to talk about an important group type. Okay, important type of algorithms called comparison-based sort. Comparison-based sort. So that means you compare the keys to sort. Okay, that means comparison sort in a word. You compare keys to sort. So you will not use some other additional heuristic information. So you use only the relation among keys, not any special property of the representation of the keys themselves. So do not use some other heuristic function about the keys. You just compare the keys directly based on this to sort to a rank, to arrange. Okay, this is another terminology, another word, another term. So next thing we want to talk about stable sort and in-place sort, though we took these two together. Okay. Stable sort means if two keys that are equal, after sorting, you still keep their relative order. Because equal, you don't need to change the order, correct? So 1, 2, 3, 3, the first 3 is equal to the second 3. So your sorting algorithm cannot change the order. Or you can change the order, but it's unmeaningful, correct? So if it doesn't change, we said this is a stable sort. Always doesn't change, don't change. Okay, that will be stable algorithm. That means we said this sorting is stable. Stable, that means you will not change the relative orders of equal keys. Okay, so in mathematical language is like this. If I is less than j, ij is the order or the place, correct? The place of the number in the original sequence. And the kpi equal to kpj. Pi, pj means their position, correct? Their position. So k means the key. So kpi, kpj means for this key, this record, their keys are equal to each other. So kpi equal to kpj. So after sorting, we also need to have pi less than pj. So that means after sorting, the position pi is still less than pj. So return the original relative order ij. So that means the ith record still appear first. So after ranking, you get a permutation of the order. Get order 1 to n will be permutated, and then you get a pi pj. So this order still have the same relative relationships as previous. So that's pi less than pj. So kpi, kpj means after ranking, you have these two keys, have these two records, their keys are the same. So their relative order has been remained. Okay, this is stable sort. So let's go down to the last one, in place sort. So stable sort, we just look at their relative order for the equal keys. In place sort, we look at the memory. We look at the space efficiency. So in place, you can just think about in place. We want to, you have a powerful sand. Okay, if you can mix them and then to be concrete, and then patch, do some patch, correct, for your driveway. You don't want to use some other place for the mixture. Then we set it in place. You may have only additional space to additional constant space. That means does not depending on how large of the pile of the sand. For example, you only use some tools, correct? If like that, doesn't depending on the size of the pile of the sand, correct? So we set it in place. In place sort means you only need a constant amount of extra space in addition to that needed to store keys. So you only need to have these two separate paths. The first one is the space to save the original sequence. The second one is only a constant number of extra space. Constant, that's the most important keyword here. That means doesn't depending on the size of the original sequence to be sorted. So that means we don't need to increase the size of the extra space if the size of the sequence is increasing. So this is the idea. For example, if the in place sort, we only need to, for example, you have n for sorting the keys, okay, and then your space, your memory space efficiency is n plus 3, n plus 5. Then we said this is in place. But if it's 2m plus 1 or 2m, that's not in place because this one will keeps increasing, correct? The n is bigger. You don't have a much bigger additional space, n, and then plus another n. That's not a constant extra space. So could you think about any sorting algorithms which is not in place that we have learned before? We learned only insertion sort and merge sort. Is it correct? Let's look at merge sort. Is it in place? No. Is it correct? Why? Because it need to have another memory to copy the sorted arrays and then to merge. So this is the size as the original sequence array. So that means it's a lot of n plus something, 2n, correct? N and then another n. Okay, how about insertion sort? Is it in place or not in place? In place sorting? Yes, it's in place. Why? Because it will not require any changing, correct? Any variable changing size. You just only to have some additional temporary memory to save the key, correct? And then insertion sort, if it's larger, if it's smaller, then shift to the right. If it's smaller, shift to the right, but you keep the original number keys in another space. After you shift all of them to the right, you have one place to insert the temporary key, that key, correct, into the place. So you don't need to. You have only constant, correct? Maybe n plus 3 or n plus something, correct? Okay, so this is the in place sort. So this is a very possible. We ask you whether algorithm is a stable sort or in place sort. Okay, in place sort, or not only like this one, maybe some other algorithm, not only sorting. We can say whether this algorithm is in place. Okay, is in place. Okay, let's look at the last terminology: array-based and list-based. So this is we mentioned before when we talk about internal, external. Array-based, you can do random access. List-based, you can only do sequential access. So that means how you save the original sequence. You want to save them into an array, that's array-based sorting. If you want to sort them based on a list, okay, so you already store all the keys, all the records in a list. When we do the sorting, you need to perform relative corresponding operations as well. Insert, how to insert a record into a linked list, so on. You need to do accordingly. So when we design the algorithms, we need to look at the input and also their data structure. Okay. Let's look at different sorting algorithms. So here we list some of them. For example, sorting by insertion, like insertion sort and shell sort. So insertion sort we have learned before. So you insert a key or number into a correct place. That's the insertion sort. Correct. Shell sort, we learned this one in the end of this slide. Basically, shell sort is an improvement beyond insertion sort. Okay, just want to improve its efficiency. Okay, next one, we'll talk about sorting by exchange, bubble sort and a quick sort. So exchange, that means we exchange the order of two numbers or two keys. So bubble sort, for example, if one is smaller than the other one, need to switch. Put the light one on the top, put the heavy one down. They're like a bubble. Bubble go up, and the heavy ones go down. So exchange. Quick sort, same idea. And then next one is sorting by selection. Sorting by selection, like the selection sort and the heap sort. So we learned this one in this slide, in this chapter for heap sort. In selection sort, we also learned before, maybe in some practice question. So basically, heap sort idea is that every time we select the maximum number among the rest, so put them, or you can say is minimum, maximum, doesn't matter, correct? So we put them, so select the maximum one, put them in the end of the array, and then select the next maximum, put it the last but one. So on and so forth till the last one is the smallest. So that's a heap sort based on max heap. Where the main focus of this module is about heap sort. So later you will learn in detail. So next one is sorting by merging. So like a merge sort. So we merge the results together to form a sorted array. So this is a merge sort. Correct? In fact, we didn't really sort the numbers and then put them into correct position. We only sort locally, but sort locally, how to sort? We do the merging. So that means one number is already sorted, and then we merge two numbers. How to merge? So we will merge the first smallest one, and then merge the larger one next. So this is based on the merge operation. We sort the numbers. Of course, this merge process also involves sorting, because you will know how to merge. You will based on order from smallest to the largest to sort, rather than just sort them directly. So this is a merge sort. And sort by distribution. So radius sort we learned before based on the probability. So in chapter 5, it involves these sorting algorithms. Okay, so for other sorting algorithms, you can click the link, and then you can find some other algorithms as well. So basically, sorting is a large group of algorithms. So you may need to pay attention to this group and then have a comprehensive understanding of different sorting algorithms. Even though you may not just have deep understanding on them, but you have some at least, yeah, just know. Okay, know we have some other sorting algorithm as well. So just click this link and then look at. Okay, if you click the link, you can find there are different groups, correct? So like the popular sorting algorithms, we have simple sort, insertion sort, selection sort, efficient sort, merge sort, heap sort, quick sort, and shell sort. And also we have bubble sort and its variants, like a bubble sort and a comp sort. And also have distribution-based distribution sort, counting sort, bucket sort, radius sort. And then you can go down to find its efficiency in the memory, right? The comparison algorithm in the table. So the different cases, best case, average case, worst case, and so on. Okay. So anyway, maybe you can look at this one later, even you are not have access to the internet. Okay, just have a look at. Okay, have a look at it on this one. I will save this Wikipedia page on the appendix, so you can download as well. So let's look at the elementary sorting algorithms. So here we talk about elementary sorting algorithms. That means basic, often to see basic algorithms, sorting algorithms we know. Usually we have such requirements, so you need to be easy to understand because they are elementary. That means the people use them a lot. So easy to understand the basic mechanism of sorting. So we understand based on this elementary sorting algorithms, we can have a easier understanding of sorting. What is the sorting? Good for small files. They are good for small files. Good for well-structured files that are relatively easy to sort, such as those almost sorted. Well-structured files, that means it's easy for you to access the key. So that means you can use the key as a bar to refer to any record. They are structured, and also most of them are already sorted. So choosing elementary sorting algorithms is basically general solution for this type of question, and it can be used to improve efficiency of more powerful methods. So though elementary basic algorithms, okay, though basic, we may use the idea here to improve some new algorithms, okay, to develop some other more powerful algorithms. So in fact, this one basic elementary sorting algorithm like the ones we listed before. So they are very popular. People use them very often. And then based on the mechanism or based on the philosophy to design those algorithms, you have a deeper understanding about what is sorting. And then how can we do the sorting in different ways. And for which type of questions this group is better, that group is even better, and so on. So that means we provide ample choices just to help you to decide which ones are better. So that means you need to have the knowledge and also understand their differences. Okay. Okay, let's look at selection sort. So for this algorithm, so basically the idea is that every time we find the maximum among the rest, and then put that maximum in the correct location. For example, if we want to sort from smallest to the biggest, correct? So we first find the maximum among the all and then put them in the end. That's why we start from n down to 2, correct? That means from the largest to the smallest we arrange. Of course, you can change this one from smallest to the largest, and then you can use the min. Do not use max. So the basic idea is that you have an array A. So it's array A. So this one is from 1 to n. That means A1 to AN. And then you start from n to 2 every time. So from here to here till you reach here. So reach 2. So there's no need to reach 1. The reason is that you don't need to compare 1 with itself, okay? There's no numbers before A1. So that means tier 2 is already enough, okay? So every time you select the maximum, so how to select the maximum? So we put I to the number here. So currently we are looking at this one is I. And then we assume this one is the max. And then we search all of the rest to see whether there's another number which is bigger than this one. If it's bigger, we replace that one with the max. Locate is location. Remember its location. Do not need to switch right now because we haven't finished the search. So that's why you can find that initially we put max to I. And after that, we search all the numbers in front, I minus 1 down to 1. Okay? Down to 1 from I currently is here. I minus 1 is here. So down to 1. So search in this direction. And then if any number A max is less than AJ, so that means this is the J. J will search from 1 till I minus 1. If there's a number which is larger than the current max, so here we will replace the max to be J. Okay, so that means we search on the rest. You don't need to search the before cat already sorted. So you just search on the rest from I minus 1 till 1, because currently we're looking at which one need to be put into the AI. That means the largest among the rest. So once we finish this search, this for loop, we find the maximum among the rest, and then we swamp the max and the AI. That means put the maximum on the AI and put the AI on the A max. So this is just a switch, nothing special. Cut. You just swamp the values. Means change the location of the two numbers. Okay. Once we finish all the loop, that means every time n, if I is equal to n, we find the largest among all of the A from 1 to n, cut. And then if I is down to 2, so if I is n minus 1, we find the second largest. I is n minus 2, third largest, so on and so forth, till 2. If we reach A2, we already find the larger one among the rest of 2. Of course, the last one will be the smallest. So there's no need to check A1 because that one must be the smallest. So it's already done. So this is the algorithm. Let's look at one example. For example, we have a number sequence is like this one, 4, 3, 2, 1. We first look at n, cat is here. Okay, look at here. We look at all of the numbers. This one from n means now we assign I to n. So I minus 1 tier 1. So which one is the smallest? Which one is the largest? We will assign that one. So we compare which one. Okay, 2 is larger than this one, so we put this max here. And then 3 is larger than this max. We put the max here. And then we will look at 4. 4 is also larger than this max, so we put the max here. So we find, okay, finally max is here. And then we will switch A1 and A4, correct? So you got the result. So this is a switch. So you got 1, 3, 2, and 4. So this is finish the first round. You arrange the largest number on the last location, in the last location. Continue the search. We put a max here, and then we search I minus 1 tier 1. And then if 1 is larger than this one, we put that one to be max. Okay, this is the max. And then this one is not larger than this one, so this is still max. And then after that, we switch this A max and AI. So we get the result is 1, 2, 3, 4. Right? So once we arrive this space, this stage, we already sorted, but we'll keep going. Right? We look at 2. Okay, 2 is as the current max, and then we search this one, tier 1. Okay, this one is not the max, so a max and A2 is the same. But for this algorithm, we still do the exchange. So finally, after exchange, which is self, we fix this max. That means the certain largest. And then it's already down to 2, correct? So we stop here. And then we check, okay, it's sorted. Okay, so this is the algorithm and one example. So overall, we can think about every time we select the largest and put that one into the correct location. Once we finish all the process, that means the tier we have only 2, we find a larger one, and then put that one into the second location. Then we sort all the numbers in the sequence. Okay. So next one, let's look at its property. So for the selection sort, so whether it is in place, is it in place? In place means the memory, correct? Whether it will have only constant additional memory. So you can just recall. For example, you go back to the previous algorithm, you can find out. So basically, you just need to have only additional space to save max I and J and T, correct? And then in addition to the memory to save A. So that's the only additional space you need to have. So if it's only like that, so it's yes, because you only need to save I, J, T, and the max. Okay. Second question, whether it's stable or not. Stable, whether you can keep the relative order for the equal keys. So go back to the previous one. Just think about whether it can do like that. Just look at here. We exchange the change the A max and AI. Whether this will destroy the original order. Just think about this. Sometimes if you want to prove something is correct, that's challenging. But if you prove something is wrong, that's much easier. Give one counterexample, correct? So make sure this counterexample will meet the requirements. So you need to have at least two keys which are equal. And then finally, after sorting, the relative order has been destroyed. Let's look at this example. For example, you have 3, 1, and then 2, and then another 2. To differentiate these two 2's, we use a circle to represent the first 2, use a square represent the second 2. And based on the previous selection sort, we have first start from here. This is ij max, I max, and then we compare whether there's another max. Okay, this is larger, so we swap these 2. So after that, we get this one. The square 2 will become the first, but we haven't finished. We don't know whether they will recovered, okay? But at least during this stage, it destroyed the order, relative order for the equal keys. Okay, that means it's possible, okay? If it retain this relative order until the end, it will be not stable. Okay, let's look at the next loop. So we look at 2, and 2 is the max. Compare this one. Okay, there's no maximum, so this one 2 fixed. And then we look at this one. So 1 and 2, this is max. So we swap these 2, and then 1 will be here. The square 2 will be here. Circle 2 will be here, and then 3. So in the beginning, we know the circle 2 in the beginning. Now the circle 2 in the end, on the later, okay? So that means it is not stable. Because we found a counterexample, that's enough. Okay, so that means it is not stable. Why is not stable? Based on one example, you can conclude, okay, or several other examples. So you can find the selection sort. It's possible to destroy the relative order during the swap between the maximum and the current elements in the AI. For example, like this one, the 2, 2 cat, they destroy this order during this stage. Okay, so that's the main reason. We didn't compare the 2 or many. Okay, didn't compare the equal keys directly. We just swap with the largest. So it's possible, for example, you have a 2, 2, they're same. Maybe you need to put a 1, 2 into correct location. So you may change that one because you're from in the end to the beginning. So you may put that one to the beginning, from the end to the beginning. So this one will destroy the relative relationship here. Okay, so that means it's just because of this reason. Okay, destroy the relative order during the swap. So next one, we do complexity analysis. For this algorithm, the complexity is always theta of n squared in all cases. From the previous example, you can also find, even though we already sorted all the numbers, but we still keep going. Even we have the max and the AI are the same, we still do the swap. Okay, we do this one before. Okay, here. So here we have two loops. So this one is sigma from I. Oh. Okay, let's go back. So sigma from n to 2, and then another sigma is from, okay, I think it's because okay, anyway, you can just think about it. It's sigma from n to 2. Another one is j is from I minus 1 to 1. So of avoid the key operation is the assignment marks to J cat is this one. So this one, two loops. Okay. So you got a result which is theta of n square for all the cases. Doesn't depending on the sorting status of the initial sequence. In fact, we can improve the efficiency of this algorithm by using some other data structure. We use a heap to store all the numbers and then develop another algorithm under the same philosophy. Means select the maximum among the rest and then put it into the correct location. That one will be the heap sort. We'll cover this heap sort algorithm in the next lecture. It has a much better complexity, which is n log n. Okay. Let's continue with another sorting algorithm, insertion sort. So for this one, we have learned before. Let's review it. So the basic idea is that we find all the elements which are bigger than the current element, and then just move it to the right. And then after we find the correct location to insert the current element, we insert that one. So you can find this algorithm. So basically we have embedded loop. So the outer loop just to find the element for each, find the position for each element to insert. So the inner loop is just to find the position, the while loop. Okay. Let's do analysis for this one. Okay. The first one, is it in place? In place, that means for the algorithm, whether we only allocate additional constant number of memory to do the sorting. Yeah, based on the algorithm, you can find we only need to have storage for A and then I, J, key, and so on, like these things. So that means it is in place. The second one, is it stable? If you go back to the algorithm before, you can find, because we have the comparison based on key and AI. Is key less than ki, less than AI? So it's not less or equal to. Okay? So that means if two elements they are equal, we will not move that one. Just change their order. Okay? We will not insert that element, that AI in front of the we will not insert a key in front of that AI. So that means it's stable. So we will not change the relative order. We will still insert the key after the location. So that means, for example, if the element which is equal to the key, we insert the key after that element. So it is stable. And then let's look at its complexity. So we have three cases: worst case, best case, and every case. So here, if A is totally sorted, so we have only theta of n comparisons. So this is we can go back to the code. You can find this relationship. Because it's totally sorted, you don't need to do the inner part of the while loop, because you can confirm. Okay, you can confirm key and AI relationship. You stop in the beginning, right? You stop it in the beginning. Key is always larger or equal to AI. So that means the key less than AI. This one will not hold. So the inner part will not do anything. So we only check the outer loop. Okay, the outer loop, the for loop. So it's theta of n. If it's totally unsorted, then it's theta of n square. So this one we have to do the analysis before as well, because each of the line 5 and line 6 will be executed for every I, till the I equal to 1, cut equal to 1. If it's randomly permuted, then it is also theta of n square. If it's randomly, so that means you can just think about there's only half a chance line 5 and line 6 will be executed. So based on this one, we still need to run the inner loop for only maybe reduced by half. So it's n by n or n by n over 2 is still n square. So the complexity will be theta of n square. Let's continue with the complex analysis. So the first one is the worst case analysis. So the worst case, so that means all the numbers are totally unsorted. When you examine one element, you need to compare it with all the elements till the end, means till the beginning of the source. So you will move all the elements in front of the current one to the right, and then insert that one to the beginning, right? Totally unsorted. For example, 4, 3, 2, 1. You need to move 4, 3, 2 to the right, and then insert 1 in the beginning, and then so on and so forth. Okay. So the maximum number of comparisons while inserting AI is I minus 1. That means all the elements in front of AI is I minus 1 number of. So the number of comparisons is based on the outer loop. So it's complexity worst case n is less or equal to sigma I from 2 to n I minus 1. So that means the upper bound. So this one will be just simplified. You can, so I minus 1, if you indicate this one as j, and then I from 2 to n, so j will be from I minus 1 means from 1, okay? 2 minus 1 is 1, and then I minus 1 till n, so n minus 1. So j from 1 to n minus 1, j. And then this one, if we do summation, will be the n minus 1 over 2. The reason is that you have n minus 1 elements, and then at the beginning and the ending elements, that's 1 plus n minus 1, that's n. So a1 plus an, and then n over 2, right? Average multiplied by the total number of elements. So this one is n squared, so it's a quadratic function of n. So it's theta of n squared. So the question is that next, for which input does the insertion sort perform n minus 1 over 2 comparisons? So we mentioned before, worst case. So if we want to sort it in a default order from smallest to largest, but what we have is from largest to smallest. So you need to swap all the elements in front of the current one, move to the right. So that is the case totally unsorted. So you will get the worst case complexity. So let's further look at every case analysis. it seems like this is the first time we are looking at more complicated algorithms, average case complexity analysis. In the past, we may just know, okay, average case for the search, linear search, so that's easier. But this one is seems more complicated. Why is it more complicated? We just finished the worst case. Worst case, that means for each element you need to swap, you need to move all of the elements in front to the right. That's for the totally unsorted. So what is the average case? Average case is in between worst case and worst case and best case. So worst case we said is totally unsorted. Best case is totally sorted. Average case means some are sorted, some are not. So some are sorted. Okay, seems like it's like a half, correct? But this is still not accurate. So half are sorted. It also can become many cases, whether the first half is sorted or the second half are sorted, or just a mixture of these two cases. We don't know, correct? So we cannot use one case to represent the average case. For example, maybe only the first half is totally sorted, the second half is totally unsorted, or vice versa. So in fact, for every case analysis, the correct way is that we will count every case, its possibility, its complexity, and then we do weighting. So that means what's the chance for each case, and what's the complexity for that case, and then we weight them together, or we add them together, correct? For example, if we dime a coin, we have half chance get a head, half a chance get a tail, and then if we have a head, we win $1,000. If we got a tail, we lose $50. Okay, you can get your expectation. So you will just, okay, $1,000 by half, by 0.5, and then minus $50 by half, means multiply by 0.5. So you got a positive number. Okay, you will always win, since if you have enough number of trials. So in every case, we consider all the contributions, all the contribution of all the cases. Okay, let's look at how to do that. So that means we need to provide analysis for a general one. For example, for each case, we need to move how many elements to the right. Okay, here let's look at the first sentence. We want to determine the average number of comparisons taken over all possible inputs. So we have mentioned before, correct? Determine the average number of comparisons. Average, just or you can think you want to get a complexity average over all the possible inputs. So all the inputs, each input have different cost. We do average. We determine the average number of comparisons for a key AJ. Okay, AJ can belong to any of the J locations from 1 to J with equal probability. So here we will look at a general case. So for example, we want to get the average number of comparisons when we deal with the element AJ. Okay, AJ, in front of AJ, we have 1 to J minus 1, okay? 1 to J minus 1. So AJ, for this element, it can be, its correct location can be anywhere, can be 1 till J, correct? For example, AJ, just the correct location for AJ, the J's location. That's also possible. And also for all of them, the chance. So of course AJ cannot be inserted into the later elements positions because they already sorted for the later for the later elements. So it can be only inserted in front, in front. Okay. So that means you can just think about AJ can be any position of these J locations. Each location has the same chance. So we set the possibility to insert AJ to any of these J locations is 1 over J. Is a uniform distribution. Uniform, that means each case has the same probability. So here we only have we have J locations. Each one is the same possibility. Add them together must be 100%, correct? So for example, we have 10 locations, and then each one is 1 over 10, means 10%. So 10% multiplied by 10, you get 100%. So that's the idea. Okay, so now we just need to understand, okay, for this one, the chance to insert AJ to any of these locations is 1 over J. And then you can just think about, okay, for each location, what's the number of operations we need to do, or how many elements need to be moved to the right. So this is the next. The number of key comparisons for AJ, is J minus K plus 1. K means the location you want to insert. Okay, so that means for this one, you need to move all the elements in between. So all the elements in between is J minus K plus 1. Is it correct? From 2 to 10, 2 to 10, 10 minus 2 is 8, and then plus 1 is 9. So totally you need to move 9 elements. Okay. If AJ belongs to location K, and then K is larger than 1, less or equal to J, so it can be equal to J and then larger than 1, and is J minus 1 if it belongs to location 1. So here you find out, okay? You find out that we exclude K equal to 1, that case. So if it's larger than 1, of course it's J minus K plus 1. And then if it belongs to location 1, it is just J minus 1. Okay. So for it is belonging to location 1, because this element starts from 1 to n, okay? 1 to n. Okay. So why we want to think out this one? So this is because of the algorithm itself. If you go back to the front, you can find the reason. Okay, find the reason. So we compare data elements with 0. That means whether it's 1 or 2 till n, and then we compare key is less or equal or less. Key is less than AI, and then we do these things. If this one is equal to 1, so this is you can, for example, K is equal to 1 if J minus K plus 1, that is not the same, correct? So J minus 1 plus 1, that will be J. So it seems not the same as this J minus 1, not same as this one. That's the key comparisons. So in fact the difference is just 1. Okay? Even you use the previous J minus K plus 1, there's no significant impact on the final result. But here we just want to have a correct number. Okay. If you look at the details before, you can find out the difference. That's a special case for the location 1. So here we consider all the cases we mentioned before. Each chance is 1 over J, and then we consider all the chances weighted by the number for key operations, key comparisons. Okay. So here we set only key comparisons, just compare. how many elements. So average number of comparisons for inserting key aj is this one, sigma k from 1 to j minus 1. That means can be any position from 1 to j minus 1. Okay, 1 to j minus 1. So that's the from 1 to j minus 1, and then each chance is 1 over j, and then the number of key comparisons j minus k plus 1. Okay, and then if it is belonging to this one is location 1, so that's also 1 over j, and then the number of key comparisons is j minus 1. So this will have all of them together. Okay, all of them together. I think this one there's a mistake. Yeah, it should be 1 k larger or equal to 1 and k is less or equal to j minus 1. If it belongs to location j, it will be j minus 1. It seems like this one, correct? Because based on this summation, it's like this way. K is from 1 to j minus 1, and then the last one is if it belongs to location j, that means we don't need to move any elements. Let's go back. For example, we go back to the previous slides, the second slide of this part, the first slide. So this one will be key, because the key is I is larger than 0, that's no problem, but the key is a lot less than ai, so that means this key is already larger than the element in front of it. That means the one element in front. For example, currently we are looking at aj, but the j minus 1, that element is already smaller, right? Already smaller than the key. So we don't need to do anything in the loop, in the while loop. That's why the number of key operations, key operation is the ai plus 1 will be assigned to be ai, and then I equal to I minus 1. That means just move or shipping to the right. Okay. So this one, I think there's a mistake. I will update the slides. So k is larger or equal to 1 and less or equal to j minus 1. And then the case location j will be j minus 1. Okay, you can expand this summation. Go back to this one. The summation, you will get these results. So due to the time, we skip the process, but we have learned this one before, correct? You just expand it accordingly. Just look at here, the k is the variable, j here is a constant, so you can single out j and then looking at k only. Okay, and then you will do the summation we mentioned before, the first element plus the last element, and then multiply by the number of elements in the sequence over 2, and then you expand it, you get this result is j plus 1 over 2 minus 1 over j. Okay, so this is the result for one simple case, general case for aj. That means in average, to deal with aj, we need to have this number of operations, that is j plus 1 over 2 minus 1 over j. Okay, let's continue with the final complexity analysis. Because for the previous one is for only one element, what's the average number of operations need to be done to do that? So here we do all the elements. So all the elements is the outer loop, correct? The outer loop from n to 2 Okay, so here we from 2 to n the same. So summing over the number of comparisons for all the kids. So it's a summation I from 2 to n for each of them is I plus 1 over 2. In the beginning, in the previous slide with j, but here we just replace the j with I, so it's the same. Only give a new name to the, because usually if it's only one independent variable in a summation, we prefer I rather than j, right? So prefer is j plus 1 over 2 minus 1 over j. Here we use I plus 1 over 2 minus 1 over j. And then expand this one. Finally, we get this second line, the results. Okay, and then in the end of this line, we have this summation 1 over I. This one we mentioned it before, you can look up and then find, okay, this is norm n. Of course, it's less than norm n. So anyway, we can find the dominating part of this equation is the n square. So we got the complexity is theta of n square. So that means the average case is also n square. So worst case and the average case, they have both the same complexity, which is n square. Okay, this is the second example analysis for the sorting. So we look at selection sort and insertion sort in this several slides. So after that, we'll conclude a general case for this sorting problem. Okay, let's look at the general analysis of the inversions in permutations. So as we learned before, in fact, for sorting, we just want to do permutations of the order, of a sequence. So we find the permutation of the initial order, and then we get the numbers, get the elements sorted. So let's look at here. We have defined an inversion. In fact, as well as in your course project, you also have the inversion. You need to count a number of inversions. So that's why we also want to mention here, cover this content. Inversion here is defined as this: a pair ij. Ij, of course, this means the order, the location. The elements I, elements j, is called an inversion of a permutation. We use pi permutation. So that means, for example, ij here initially is ij. After sorted, you get in fact you just correspond to a permutation. You get a sorted order. For example, initially 1, 2, 3, 4, 5, the elements order. Now you got 5, 4, 3, 2, 1. So that's a permutation of 1 to 5. So we define this permutation from 5 to 1. It's the sorting process, the results. That's the pi. So what it means is inversion. Inversion, that means the original order is ij, but once you sort it, you get this: if I less than j and pi I is larger than pi j. So that means a pair. For example, initially we from I to j. I means the smaller one, j is bigger one. So initially I is in the beginning, j is in the end. But after permutation or after sorted, you assign a new order. The new order change their relationship. The pi I is larger than pi j. That means you will rank the ith elements in the end, just after the j's elements. because pi j is smaller, means its order is in the beginning, cut is in the front, and the pi I is in the has a larger value, means we put that elements to the rear, move the jth element to the front. So you change their relative relationship, the order. For example, initially the element I is in the beginning, after permutation I is in the end. Okay, that will change the ij relationship. And then the worst case for algorithm, for sorting algorithm, is n minus 1 over 2 inversions. So that means we need to correct this number of inversions, then we can sort all of them. So this is a totally unsorted case. Correct? What's the case? So it means all the pairs are a case of inversions. So that means that all of them are totally unsorted. So that's the for this one. Then for order permutation we have, of course, is just reverse, correct? Reversing. So for this special case, totally unsorted, then we need to use the reverse of all the orders. You get this one from 1 to n, and then you from n to 1. Just rank all the elements. Okay, so initially 1 to n, 1 to 3, 4, 5 till n. Now the permutation will be n minus 1, n minus 2, till 2, till 1. So let's look at the average case. Worst case, it seems, that's very special. So what's the average case? So in fact, here we give a proof for average case. You can look at the end of the results. The average number of inversions is n minus 1 over 4. So it's just 1/2 of the worst case. So how to prove this one? So basically, prove this one, we use a method based on the transpose of the permutation, and then we count how many possible inversions in both the original pi, the permutation, and the transpose, and then we do the average, just divided by 2. This is the basic idea. Let's start with the first item. Let pi transpose equal to pi 1, pi 2, pi n be the transpose of pi. Transpose means you totally reversed the permutations. For example, initially it's 1, 2, 3, 4. So you do the transpose, you get 4, 3, 2, 1. And then let's consider the pair ij with I less than j. They are n minus 1 over 2 pairs. So here means what? So that means we consider all the possible pairs in this sequence, because this is like choosing 2 from n. So you have choose 2 from n, you get n minus 1 over 2. So this is a pair. Okay, the number of pairs. So ij is the inversion of pi if and only if n minus j plus 1 and n minus I plus 1 is not an inversion of pi to the transpose. So this is in fact is easy to understand, correct? So that means pi is the original permutation. Pi to the transpose is totally reversed. So if originally ij is the inversion, and then if we totally reversed this pi permutation, so in its transpose, that ij will be not inversion, correct? So that means this is exclusive. You can just think about their equivalent to each other. For example, initially, if we rank 2 and 4, 2 and 4, there's no inversion. 2 is in beginning, 4 is in the end. If we reverse this one, you get 4 and 2. So there's an inversion in the transpose. vice versa, right? If there's a inversion in the transpose, then there's no inversion in the original source. Okay, so this is the idea. This implies that the pair pi and the pi 2 transpose together have in total n minus 1 over 2 inversions, because that's the total number of pairs that's possible. We choose two different numbers, I and j must be different, right? So that means this is based on the second claim. So that means in pi and pi transpose altogether you have n minus 1 over 2. That's all the possible pairs. All the possible pairs. Okay. Number of pairs which can be inversions. Okay. This implies the pair. This is 2. So because one is inversion, the other one is not. So how many cases you have in total? It will be n over n minus 1 over 2. This you have these only combinations. If this inversion appears in pi, then will not appear in pi to the transpose, vice versa. So how many combinations altogether? It is this number, because 0 plus 1, 1 plus 0 is still 1. You count only one time. So how many counting? In total, you have n minus 1 over 2. That's the total possible combinations. You choose two numbers from this any two numbers, right? Any two numbers from this sequence pi. Okay, so that's the pi and the pi transpose in total have this one. Then the average number of inversions is half. That means yeah, you consider all the cases. Some appears in pi, not appears in pi transpose. Maybe 0 and then n minus 1 over 2. And then 1, and then that one is minus 1, correct? For example, we have 10 cases, 0, 10, and then 1, 9, 2, 8, 3, 7, and then 5, 5, 6, 4, till 10, 0. So you average all the cases together, which will be 1/2, means 5, 10 over 2. So that's the reason, correct? Both they are equal, correct? Pi and transpose. In fact, we can think about they are equivalent to each other because they are just correspondence. So the average number of inversions is this one. So every case you will have this number of inversions. So your sorting algorithm has to correct all the inversions, otherwise it's not sorted, correct? So that means your algorithm will correct all the inversions in the every case, worst case. Okay, that's based on these conclusions, we have a proposal. Okay, continue with the previous slides. We want to, based on the previous conclusions, we propose a theorem. This theorem is doing like this. Let's read it. Any algorithm that sorts by comparison of keys, means the comparison based sorting, correct? And removes at most one, so that means the algorithm will remove at most one inversion after each comparison. At most one inversion. For example, during one round of comparison, you may remove one or just correct one inversion or none, correct? At most one. After each comparison, must do at least n minus 1 over 2 comparisons in the worst case, and at least n minus 1 over 4 comparisons on the average. Okay, so this is easy to understand, correct? Because you can think about, we based on only comparison to do the sorting, and then in total we have concluded before in the previous slides. In the worst case, we have n minus 1 over 2 inversions to be corrected, and then In the average case, is over 4, correct? Previous is over 2. This one is over 4. Inversion to correct. But each comparison can only correct at most 1, less or equal to 1. Of course, if you divide the number of inversions by 1 or 0, of course not 0. That means each time you only correct at most 1. So you need to get how many rounds to finish the correction. So that means at least, correct? At least. If it's equal to 1, then that is the minimum number of comparisons you need to do. If you correct less than 1 sometimes for one comparison of 2 keys, then it will be more than this minimum number. So this will be very important, because you can find if you only based on comparison and each time you only clear 1 or 0 at most 1 inversions, then your complexity will be there, okay? At least means a lower bound. So you can find the lower bound is both of them are theta of n square. So that means your comparison algorithm cannot be better than quadratic complexity for this comparison based algorithm. If you can only clear at most 1 inversion in each comparison. So for such comparison based algorithm, we can expect its complexity will be at least theta of n square. So this is the important conclusion we have here. So if you want to improve this algorithm, what you need to do? You need to reduce the number of comparisons, correct? So what we can do is that each time during one comparison we clear more inversions, then we can reduce, correct? We can reduce the complexity, reduce the number of comparisons needed. If you can only clear 1 or 0 inversion each round, then your complexity will be always larger or equal to theta of n square, correct? So this is the conclusion in the end of the slides. So if we want to do it better than theta of n square, we have to remove more than a constant number of inversions with each comparison. Let's continue with the shell sort. This is based on the previous motivation. That means we have to clear more than 1 inversion during one comparison. So basically, shell sort is not completely new. It is a simple extension based on the insertion sort. So that means the insertion sort we have no, and each comparison, each round, each separate comparison, right? We can sort one number. So we may correct one or more inversions. So we, based on this insertion sort, we develop the shell sort. So let's look at its idea, and then later we'll give you an example on the board, on the just a demo. So this one we gain speed by allowing exchanges with elements that are far apart, so thereby fixing multiple inversions. So what's the meaning here? So that gain speed means reduce the complexity or increase its performance. We can allow exchanges. That means we swap the positions of 2 elements, correct? Exchange. So insertion, we just move to the right and then insert. But here you can find we allow exchange with elements that are far apart. So that means we may just exchange with some elements which are far from current location. Okay. And then during this round, we may just do several. We can clear several or fixing several several insertions. So what's the basic idea? Shell, you can think about it like a layer by layer, correct? So you can just think about if we have a sequence, can we chop them by some jumping steps and then generate several subsequences, and then for each subsequence we can do the sorting. So this is the idea. So we call the h-sort the file. So you can first divide the file into h subsequences. Each subsequences consists of keys that are h locations apart in the input file. For example, if h equal to 5, so the first one is A1, the second one will be A6, correct? H part, so you plus H plus the steps, okay, and then next one will be H and A1 plus 5 plus 5, that's A11, correct? So 1, 6, 11, each two has a step of 5. And then third step, you sort each H sequence using insertion sort. So that means we generate H layers, correct? And each layer will be using insertion sort to sort. So this one will result in H sorted files, taking every H key from anywhere, resulting in a sorted sequence. So that means if you jump in every H element, you will generate a sorted, you will have a subsequence, correct? Subsequence, you using insertion sort, you get a sorted subsequence. So but every H you need to jump. So though as a whole is not sorted, but if you jump over H every time, you will get a H sorted file, H sorted subsequence. So next one, H sorted the file for decreasing values of incremental H with H equal to 1 in the last iteration. So that means we have generated H sort file, okay? H sort the file. So next one, we reduce the H and then increment H. H can be different numbers. So H, if it drop to 1, so totally is sorted, correct? So this means when we do the sorting for each one, we can say H sort. For example, if we use 5 as steps, and then 3 as steps, 2 as steps, 1 as steps. So we use this several H sorted file to do the sorting. Just reduce the H, and then each time we make the sequence more sorted. For example, we first use 5. Okay, every 5 elements we sort a number sequence, every jump 5. After that, we reduce it by maybe by 2 to 3, correct? And then to 1. So that means each time we do less and less exchange, because many they are already sorted. So the only remaining part is very few. So this is the basic idea from cause to find. First we adopt a cause step, and after that we reduce it to find till 1. 1, that means it's just like insertion sort. It's the same insertion sort, but now you are doing an insertion sort on an almost sorted sequence. So the last step will be very quick. Okay, let's look at last about one item. H sorting for large values of H in early iterations reduce the number of comparisons for smaller values of H in later iterations. So that means you use a course. So for example, if you want to cut a tree, you first use a chainsaw to cut the stem, and after that you cut branches and so on. So that means in the initial part, initial stage, you will reduce the work for the later. So you don't need to use a small knife to cut a stem. Okay, that will be the important idea for this thing. So you can just keep less and less insertions for the later stages. Because if the step is small, you may need to compare more elements. Is it correct? You jump over 5, you jump over 3. So jump over 5, you like a sample. You have less elements. Jump over 3, you have more. So if you jump over only 1, you have the most number of elements to compare. So that means later we have less and less insertions to correct. So this is the idea. So the last one, the correct list, follows from the fact that the last step is plain insertion sort. So as long as you have a last step which choose h equal to 1 jump step, you will make it correct because you have proved the insertion sort correctly. So this last step is just insertion sort. So of course, always you will have a correct sorting results. You can look at the Wikipedia to know more about shell sort. But anyway, we'll continue with some examples, and also analysis. Okay, let's look at further about the shell sort. So basically, this algorithm is a family of algorithm. Means we can choose different jumping steps. So that means it's not only one choices, because you have many options. So that will define a family of algorithms. So it will be defined or characterized by the sequence HK of increments that are used in sorting. So that means depending on different sequence HK jumping steps, you will get a different shell sort algorithm. Though the algorithm is the same, but you can choose different jumping steps sequence. You will get a different specified algorithm in this family. Okay. So we also mentioned this before, why it is easier, why it is more efficient. So by interleaving, we can fix multiple insertions with each comparison. Because you jump from one location by h steps to another one, you can reach some elements which is far from your current one. So that later passes means, for example, reduce the jump steps. Later passes will see files, means h-sorted files that are nearly sorted. So I'm almost sorted because you have fixed multiple insertions in the previous comparison. This implies that either there are many keys not too far from their final position, or only a small number of keys are far off. So that means after the initial processing, many elements, many keys are already almost sorted, so just very close to their correct location, final position, or only a small number of keys are far off. Okay, let's look at one example. So we don't have a blackboard, so I will show the notes here. So here, assume we have a sequence from A1 to A1 to A10. Okay, so this is A1 to A10. Okay, so this one. So basically, we give a very special case is totally unsorted from 1 to 10, but from here is 10 to 1, correct? Totally unsorted. If we choose a H sequence like this from 5 to 3 to 1, and then let's look at how we do the sorting. Okay, do this shell sort. First one, we use H equal to 5. So that means every time you jump 5 locations to find the next elements in that subsequence. Okay, so that means here from A1 you will jump to A6. Okay, A1 to A6. So let's look at, we can use A1 and then to A6. So you have 10, and then next one is 5 plus 5 more, you will get 11. That is out of range, so you will not have that one. So in that tick 1, that's one sequence. And the next one we start from A2. So A2 you add 5, you get A7, correct? A7, A2, A7, and then you add 5 more, you jump to the other one. So similarly, you have A3, and then add 5, you get A8. So that's the circle. And then you have a square, A4 and A9, and then the upside down triangle, A5 and A10. So that's the five subsequences we obtained based on the jumping step H equal to 5. And then, so for this one, we need to do sorting, correct? We need to do sorting. So after sorting, what will be the result? So for the first subsequence, A1, A6, the tickle one, correct? The tickle one. So you need to use insertion sort. Okay, we will compare A10 is larger than A5, 10 is larger than 5, so you need to shift 10 to the A6, so jump to here. So put the 10 into A6 and then just copy the key to the A1, correct? So on and so forth for A2 and A7. So it's 9 and 4, so you got 4 and 9. And A3 and A8, you got 8, 3, so you sort them, you got 3, 8. And the A4 and the A9, you got 2, 7, 2, and then you need to get 2, 7. And then A5 and A10, you have 1, 6, 6, 1, correct? You got 1, 6. So this is after one round, okay? One round of H step, you use the shell sort, this loop. So you can find, you have sorted a lot of numbers. For example, you have sorted 5 subsequences based on this first round. Same using the same method, you choose H equal to 3, and then you can do similarly. So A1, A4, and A7, A10. So for this one, you will do the sorting, correct? You will do the sorting, and then after that, you get these results. Is 2, 1, 3, 5, 4, 7, 6, 8, 10, 9. You got these results. So you can find that we also use different marks to indicate. So tick the ones. So 5, 2, 9, and the 6. After you sorted, you got a 2, 5, 6, 9. Correct? So tick ones, and then triangle ones 4, 1, 8. After sorted, you got a 1, 4, 8, and circle ones 3, 10. 3, 10, and 7. You got 3, 7, 10. Okay. So after last round, you can find you only need to change a little bit. Cut just 2, 1. You got 1, 2, and then 4, 5. You change it to be 5, 4. You got 4, 4, 5. 7, 6. You got 6, 7. 10, 9. You got 9, 10. So you can find after we've performed 2 rounds, it almost sorted. Only need to change 4 inversions. We can reach the final sorted array. So that's how it works, cut. Because when you do, you can think about when you jump and sort it. So if you change 2 numbers based on this comparison, you only change, for example, 10 the first round, 10 and 5. When we choose H step to 5, 10 and 5, you move 5 to A1 and move 10 to A6. You already correct a lot of inversions there. Is it correct? For example, 5 should be after, correct? After 4, for 1, 2, 3, 4, and all of the numbers which is larger than 5 should be after 5. So you can find that, okay, 9, 8, 10, like all of these things. After you do this jump, so all the numbers after 5 is already yeah, in the later, not in the front. And then you put a 10, same as the 5. You put a 10 to A6. So all the numbers which are smaller than 10 need to be in front of 10. So you have correct how many? So that means before A6 you have 5 numbers. So for this one comparison, you already correct 5 inversions there. So all the numbers which are less than 10 have been, of course, not only one. After you perform this round, so you have 5, 4, 3, 2, 1. All of these 5 numbers are in front of 10. So that means the inversion has been corrected based on this one. So that means this will be much more efficient than the insertion sort. Insertion sort, every time, for example, if it's totally unsorted, each time you will move this 10 by only 1 location. It's correct? For example, first one you need to move 1 in the beginning, but you only shift 10 by 1 location to the right. For this, how many comparisons? You compare 2 to the 10, 9 comparisons, but you can only correct 1 inversions related to 10 to A10, correct? To the A1, which is 10. So this is how we improve the efficiency. We improve the efficiency by cleaning more inversions based on 1 comparison in average, correct? In average. Okay, that's all for this example. Just look at the example by yourself and then let me know if you have any question. Okay, let's look at the pseudocode of shell sort. So basically this one is the pseudocode. We use different colors to indicate different parts of the pseudocode, and also is very structured, well structured. So basically it's a shell sort A to N, okay? A is the array, N is the size of the array. And then for the first 4 lines, we do H equal to 1, and then Y H less than N, H equal to 3H plus 1, and so on. So you can just think about, for example, N is equal to 10. So H is started from 1, and then H less than N, you increase the H every time by 3 times plus 1. So you got the next one will be 4, and then next one will be 13. Okay? 13 is not less or equal to N, so we will stop. H can be only at most 4. So when we deal with a sequence which contains only 10 numbers, so this H just want to help us to define a sequence. You need to find the largest one. Okay? This is the largest. Find the largest one. The rough we said is coarse to fine. So find the largest H, and after that we reduce H every time by 3. So that's the line 6. Here we reach H equal to 1. So the structure is very clear cut. So that means here we just want to find the largest H first, and then after that we sample the sequence, sample the original sequence to get a subsequence, and then apply the insertion sort on the subsequence. That is this is the sample cut H. You decide the sample steps, and then you do the insertion sort, which is from line 7 to line 16. You do the insertion sort. Okay, that's what we need to do. First one you sample. Second one we do the insertion sort. In fact, this one when we do the sample, we only choose the sample steps, and then in fact generating the sample the subsequence is integrated with the sorting. How we do that? You can find here we jump every time by H. Okay? So that's how we do it. Okay, let's look at the line 7 to 16. This is familiar to us because we have learned this one before. Do you think so? For example, for I, we mentioned before, it's just insertion sort H to undo this one, and then we assign key to AI, and then J to the I, and then move J by H every time. If there's a number which is larger than key, we need to shift that number to the next, to the right, means J minus H to the AJ, and then we move J forward. Okay, if J is less than H, we then break. So this is different from previous. In the previous we have the J is larger than 0. Okay? So here is J less than H, means this one we don't need to compare, okay? Because that's if J is already less than H, you cannot find another AJ minus H, because it's J minus H will be negative, is out of the range. So this one will make it stop. Okay, similar range check as the insertion sort. Okay, after you reach the beginning, the last elements in the subsequence, or you can see the first element in the subsequence, the first one, and then you can stop, or you find some elements which you will not make this hold, then you can stop. Okay, or you can move, you can shift. Okay, you can shift, and then last one you insert that key to the J's location. So it's exactly the same as the insertion sort. Let's go back to the insertion sort. So here you can find, so this is insertion sort. Okay, so J is from 2 to n, and the key, this is the AJ. Okay, and then J minus 1. So compared to the elements in front of the key, it means the J, correct? The AJ, and then you examine all the elements in this before the AJ. If it is larger than key, and also not reach the end, larger than 1, then 0 means at least 1. Then you shift this one, shift this AI to the next. But for us, shell sort will to the next step. Okay, after jumping H. Okay. So, and then we keep going. Okay, and then after that if we found move shift all of them, then we find a location, we insert that element to that the key elements aj to that location. Okay, this is insertion sort, exactly the same here, cut. So we have this similar. So h j I is from h to n. Okay, h to n. So the reason is that at most you can reach h, and then if h you minus h, you will get 0, right? Because we sample this one from the end to the beginning. Okay, so this is the reason. So this is the lower bound for the subsequence. They can only from h. Okay, and this is the same cut. So we first assign the key to be ai, and then j just to indicate the elements. Okay, ai, and then from j here we not use I minus 1. I minus 1 we use j because we need to use this j to calculate next element in the subsequence. Each time we jump to the beginning of the sequence by h. So aj minus h. Compare this key and this one. If it's larger, then shift this aj minus h to the aj, and then j move to the one more before, cut to the next, means to go into the front. If j already less than h, then break. We mentioned that you don't have a chance to jump over because you will reach negative values. So this is the ending, or this is the ending condition. Break the while loop. After you shift all the elements which are bigger to the right location in that subsequence, you insert the key into aj. That will be the right position to insert a key, right? Okay, go over this one and then choose another h till you reach h equal to 1. So that means h equal to 1. That's the last round. This one, for example, divided h equal to 4 divided by 1 time by 3, you get 1, and then you reach 1, right? So this one you get already 1. So that's the last step. You have performed the real insertion sort. So when h is equal to 1, this is the insertion sort. Otherwise, perform insertion sort on keys h locations apart. H values are set in the outermost repeat loop, and then they are increasing, and the final one is 1. Okay, this is the pseudocode for the shell sort. So overall, you can think about this is just the extension of the insertion sort applied on a set of subsequences. But what's the performance? Why we need to do this? Cut, we make it more difficult seems. So whether we have some benefit by doing this? Okay, let's look at its analysis. First one, whether it's in place. Yeah, it's in place. It's correct because you can find that we don't apply for another n space to save a again, like the merge sort. So it's in place. We only need to save to allocate additional story to h, I, j, and key, right? Like these things. So that's only constant number for additional storage. So it's in place. Is it stable? No, not stable, because the insertion sort is not stable. So of course this is also not stable. So same reason. Okay, so next one we want to talk about the complex analysis. Here we conclude like this, because you can choose different subsequences to sample the original sequence. So the complexity analysis will be very complicated because it depends on the sequence of increments. So that means how you, for example, you choose a 1, 4, 7, or you choose a 1, 3, 6, and like this one, you will get different results. So really, it's more difficult to do that because you need to add all the h together, correct? Like previous, we have the h equal to 3 to 5 to the example we mentioned that example h equal to 5 to 3 to 1. You need to add all of them together, and then you get the complexity, and also depending on the subsequence. So that's beyond our scope. Okay, just understand. Maybe this is not an easy problem. You need to, just like you need to do a several complexity analysis, and then add the complexity together to get the final one. But if we choose some special series for the sequence, for example, like this one, is 2 to the power of k minus 1. Means k equal to 1, you got a 1. K equal to 2, you got a 3. K equal to 3, you got a 2 to the power of 3 is 8. 8 minus 1 is 7. Right? 1, 3, 7, and then 15, 31, and so on. So like this one, we can get the complexity because this one is the simple case. So you got a 2 to n to the power of 3 over 2. Okay, seems better than the previous one. Is correct. Insertion sort, we have a theta of n to the power of 2. So it's quadratic. This one is 1.5, which is less complicated. So that's the why we want to do the shell sort, because it clear more, like we mentioned, clear more inversions during one comparison, because you jump over, you can move the numbers quickly, so you will clear more inversions based on only one comparison in average. Okay, so in fact this is the last slide of this introduction slides. So you can think about, we have a trade-off. We have a trade-off between the theoretical analysis and the concrete algorithms, sorting algorithms. Here we have more detailed theoretical analysis, but we only cover only one sorting algorithm, which is a heap sort. So that will be the lecture for next week.